From the beautiful studios of Way Happy, this is Mr. Meyer and 3.3 log functions and their graphs. All right, think about what you know in math. You know that 3 times x is 15. You know how to solve that because you know, they're multiplied together with the x. I'm going to divide by 3. And because division is the inverse operation of multiplication. And so that's how you're able to solve it. If you look at the second one there, you subtract 2. Why? Because addition and subtraction are inverses. Squaring and square rooting are inverses, right? Well, what about exponents? Who is the exponent inverse? And that is our beautiful thing, logs. It is very important to know that logs are the inverse operation of exponents. So now, how do we go ahead and work on that? Well, first thing you want to learn is how the heck do you even read a log? And that's what we're going to do in this little section. And so let's get started. First thing I want you to know is that here is exponential form. We call this exponential form, and you could probably guess why. And we call the other one log form, and you could probably guess why, right? And so those are the two forms. Now, what's one thing I always stress to everybody about the two forms is that a little bit of vocab comes in. Every log has a base, right? And every power has a base. And one thing you should notice every time you do this is that the bases should be the same number. If it was an exponential form, then when I write it in log form, I know it's going to be the same base. That number will be after the word log. Now, other than that, the other thing that I like to remember is that since logs are inverses of exponents, the way I think of it is the word log says it tells me what the exponent is. So if you notice, this is telling me the exponent was a y. And if you look over here, the exponent was a y. So when I convert back and forth, two things I look at. What is the exponent? And I look at what is the base. And that usually gets me through everything else. I also had a teacher who once taught me the way you read a log is, say you have log 3 of 2. And the way they would have me try to rewrite this would be something like the exponent you put on 3 to get a 2 is blank, right? So they would say the exponent, and I liked that, but it was confusing at first. The exponent you put on 3 to get 2 is x. That's the way she would translate every sentence like that every time she did a log. All right, let's try the two ways. So if you look down here at the first example, we have my teacher's way, who she would say the exponent you put on 2 to get 8, and then we would have to answer that. Or maybe we have to rewrite it in another form or whatever. So the exponent you put on 2 to get 8 is, I don't know. That's what she would tell us. And then we'd have to figure out, oh, it's 3. And we'd be all excited that we figured it out. If you use my base method, you would be like, all right, well, I know the base is 2. So the base is 2. I don't know what it's equal to, so I don't know what the exponent is. And then whatever 2 to the exponent is, you get 8. And then you calculate from there. You hopefully write that 8 is 2 cubed. And then you're like, oh my gosh, if it's 2 to the x is equal to 2 cubed, then x must be 3. Done, right? Same thing here on the next one. 5 to what power is 1 over 25? And I'm like, oh, it's -2. So this was just a fancy way of saying -2. So when I mark something wrong on a quiz, instead of putting -2, I could put log 5 of 1/25. And you should be like, oh, I missed 2 on that problem. What a bummer, right? Or in basketball, back to the first example, when a guy makes a three-pointer or a girl, instead of saying, hey, three-pointer, they could be like log 2 of 8. Well, log base 2 of 8. Is how many points he just got for that shot. And people would be like, what? Crazy. It is just another way of saying that number. It's nothing fancier than that. All right, what kind of properties do you need to know about logs? There are a couple. That you have log of any base of 1, it's always equal to 0, because think about it. That's saying b to the 0 power is 1. I don't care what b is. So of course that's true, right? So if you ever see log b of 1, log any base of 1, you know the answer is 0. If you see log base b of b, well, then you right away know that that's a 1, because it's the same thing as saying, b to what power is b? Well, the only one that works there is 1. So make sure you understand when it's 0, when it's 1. Log base b of b to the x is x. And that makes sense because b, if I rewrite this one, it would be b to the x is equal to b to the x. Well, yeah, then the exponent is the same. And last but not least, the other way around, and that one might need another property for, but since exponents and logs are inverses, then those inverses would cancel each other out and you would just be left with x. So very important to know, because then it makes some problems super duper easy. So here it is. Look at this, log 3 of root 3. I could rewrite log 3 of root 3 as to the 1/2 power. And then if you know some of those properties up there, specifically this guy, right, then I know that logs and exponents, the logs and powers, they're going to cancel each other out, and I'm just going to end up with the half. And that's it, right? If you wanted to rewrite it, you could have. You say set this equal to some variable m for Meyer, and then I rewrite this as the base is 3, the exponent is m, and it's supposed to equal whatever came after the word log, which is 3 to the half. And then at this point, I should be able to view it and be like, oh, m's a half, So either that they're inverses and they cancel each other out, or you can go ahead and do the math. Either way, you are a rock star. Something you want to know is that logs of base 10 are called common logs. So if somebody just writes the word log, it's understood that it is base 10. So, like in math, when we have 1x, we don't really write that anymore. We always just write x, right? Well, same thing with logs. Everybody got sick and tired of writing log base 10. So they said, all right, if we just write log, that means base 10. Otherwise, if it's a different base, we'll write something else. And so they do. So like this is log base 10 of 1 over 1,000, which at first you might think is really tricky, but what is that? That's log base 10, which no one would write. They'd probably laugh at you, but I'm going to do it for this one. And then what is that? 10 to the third is 1,000, so that's 10 to the negative 3. All right, and look at log 10 and 10 cancel out. That's just a fancy way of saying negative 3. Oh, look at this. This is log base 10 to the 1/5. Well, I know what happens to log and 10. They cancel out. That's 1/5. And you just want to be that quick. Beautiful. Let me ask you a question about common logs, and I'll come back after that break. Great effort you showed on that last one. All right, good job. Now, just like there was a common log, there's also a natural log. And what is natural log? Well, remember Euler's number? Euler's number is that weird 2.71828818. We use that for continuous growth or continuous decay or anything like that. Well, a lot of times it'll work out that we need that for our base when we're trying to solve problems about bacteria growth or something like that. So we use log of Euler's number a lot. And so since it happens a lot, when we have log base E, people got sick of writing that too, and they just called it natural log. Well, look, it's a little backwards. It's ln. Log natural, as the French would say. But that's all it is. It is natural log. It's a button also on your calculator, just like the log button is on your calculator. And so just so you know, natural log is log base E, used a lot because it's quicker to write. It's only 2 letters instead of 3. I mean, it's nice. Natural log is a nice thing to have. So if you look at my example here, which isn't in red, that makes me sad. What that would be is natural log of e to the 1/4 power. And then I'd be like, oh, I remember these properties because they hold true for natural logs just as well. Natural log is what e's inverse is. And so therefore the answer is 1/4, and I jump up and down. And that's it. That's natural log. So you can do a log base 2.7, but everyone would laugh at you. So, all right, graphs of logs. There are 2 graphs that you want to know. So in chapter 1, when we talked about graphs, all I really kind of said was, hey, look, there's an asymptote, and then you go to the right one, you make a point, and then that's good enough for your logs, right? Actually, sometimes you could get a second point in there too, but that's good enough. That's what a log looked like. Well, that was true if the base was greater than 1, which is something we would usually deal with. But a little heads up, if the base isn't less than 1, kind of like there's a growth and a decay graph, since these are inverses of those guys, well, there's also a little flippage when there's bigger than 1 and between 0 and 1. And so you can see the 2 pictures there. When the base is bigger than 1, we have what I sketched to the right. But if we have the base less than 1, then all of a sudden we get this reflection. So a little heads up, be careful on that. All the usual transformations go on logs. And so don't you worry at all about any of that. So let's try to sketch a couple logs. So I'll give you this first one here. If I'm going to sketch this bad boy, so in the back of my mind, I see that this is a natural log. So that's log base E. So that means it goes like this, right? Well, but notice some things like you're probably screaming at me, no, 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 there's a negative in front. So I got to flip it over the x-axis. So you're right, but in the generic form of it, I was thinking like that. But I do have to flip it over the x-axis. I do have to move it, looks like right 3. So here would be my actual graph of this bad boy. I'm going to flip it over the x-axis first because I do my stretches and shrinks, which flips are. And then I'm going to move it right 3, my translation. So there's the right 3. Now from that spot there, remember you could go right when there's that point right there. And then instead of going up and to the right, I'm going to come down and to the right. And boom, there is my sketch of what that graph would look like. Beautiful. All right, try the next one. Same kind of thing. I'm going to come over here and I'm going to draw my graph paper. And I'm going to notice some things like, oh, it's already 0.4, right? So that means it's this weirder graph. It looks to me more like this. All right. And let's see, it's stretched vertically, and down 5 is about all I see. So I have my asymptote did not move because it wasn't shifted left or right. However, that one magic point that I would usually put right here, I'm now going to put down 5, 1, 2, 3, 4, 5. And then I'm going to go ahead and graph that graph. So there's my logarithm that has a 0.4, and it is now graphed. How about a super tricky one then that has a bunch of tricks or a bunch of messes in it? This guy, right? So first things I would do is I don't even like the way it's written. So I'm like, all right, I'm going to write this as log of negative x plus 4 plus a 1. I like to have the log first, and so I'm like, oh, it's up 1. Now, a lot of kids might think that this is a left 4 shift, but be careful. We are way more clever than the average Joe, and so we know to factor out that negative 1 because we want to see what's happening to the x, and all of a sudden we have discovered that it is actually right 4. But there's other things going on like that negative, meaning flip it over the y-axis. So this is a log base 10 graph, right? So he would look like this. But he's flipped over the y-axis, so he's actually going to look like this. But no big deal. So that's the y-axis flip. Then I'm going to move him right 4 units. So we're going to move him right 4, and then we're going to move him up 1 because those are the other shifts. So right 4 means my asymptote is moved right 4. And then remember that the magic point would be over here, but I went up a little bit. It would actually be on the line, but because it was reflected, it's actually on this side. So it'd be there, but oh wait, it's up 1, so it's here. And now I can finally sketch my graph. I'm going to start down here and I'm going to go like this and out of here. And there is my log graph as I shifted it right 4 up 1. And I'm very happy. And you can see that 0.31 on the graph. That's on the graph. If you check Desmos, it will be. Beautiful work. Now let's see about measuring sound. That's the last thing we have to talk about. You've probably seen on a stereo somewhere a decibel reading when you crank up your stereo and it tells you how loud your music is, some weird number. That is actually just based off of logarithms, really. And so here's the equation for it. If you want to measure decibels, then what you are doing is 10 times the log of the sound divided by our hearing. And that will just tell you how loud it is. So here in the question I ask you, how many decibels is a subway train? Well, here's what a subway train is. Here's what our ear can handle. And so I would just do 10 log and then the subway train, which is 10 to the negative 2 over 10 to the negative 12. And that is what the stereo calculates and then tells you how loud your music is. So what is that? That's 10 log. Now, just quick exponent subtraction. If they're the same, you subtract them. So it's like 10 to the 10th. And then we just did a bunch of this. What happens when you have log base 10 of a 10? Cray, cray, they're gone, right? And so now this 10 is just going to come down. So we have this original 10 and we have this 10. So that's 100. So we're talking a subway train is cranked up to 100 decibels. Oh, that's loud. And it's time for me to go to bed. You have a great day. I'll see you tomorrow. Stay happy.